There is a language older than every civilization that has ever existed. Older than Sanskrit. Older than Sumerian. Older than the first sound any human mouth ever shaped into meaning. It was here before language, before biology, before the first atom assembled itself out of the chaos of the early universe. And it is still here, running underneath everything you see, everything you touch, everything you are. It is not hidden. That is the strange part. It is not buried in a temple or encoded in a sacred text or locked behind a door that only initiates can open. It is the most visible thing in the universe. It is in the spiral of a galaxy and the spiral of a seashell, in the ratio of your heartbeat and the ratio of a planetary orbit, in the geometry of a snowflake, the branching of your lungs, the frequency of the light that allows you to see these words right now. The language is mathematics. And before you close this window, before the word mathematics triggers whatever residue of boredom or anxiety your schooling left behind, understand that what we are about to discuss has almost nothing to do with what you were taught in a classroom. The mathematics you learned in school was a tool, a set of procedures for solving problems that someone else defined. What we are talking about here is something entirely different. We are talking about the possibility, taken seriously by some of the most rigorous minds in the history of physics, that mathematics is not a tool we invented to describe the universe. It is the substance the universe is made of, not metaphorically, not poetically, structurally. That the equations physicists write down are not approximations of reality. They are reality. That the reason mathematics works so unreasonably well at predicting the behavior of everything from subatomic particles to the large-scale structure of the cosmos is not that humans are clever. It is that the cosmos is mathematical, that the deepest layer of existence is not matter, not energy, not consciousness, not God, but pattern, structure, number, relation. This idea is 26 centuries old. A man on a Greek island proposed it before anyone had built a telescope, before anyone had split an atom, before anyone had any reason to suspect that the universe might be anything other than what it appeared to be. Solid, physical, made of earth and water and fire and air. He said no. He said the universe is made of number. He said that beneath the surface of everything visible, there is a mathematical order that is more real than the objects it produces. His name was Pythagoras, and for most of recorded history, his claim was treated as mysticism, as philosophy at best, as nonsense at worst. A beautiful but ultimately naive idea from an era that did not yet understand how the world actually works. And then the 20th century happened. Quantum mechanics revealed that particles are not objects, but probability distributions. Mathematical functions that collapse into physical reality only when observed. General relativity revealed that space and time are not containers, but a geometric fabric whose curvature is described entirely by equations. String theory proposed that the fundamental constituents of reality are not points of matter, but vibrating filaments whose properties are determined entirely by the mathematics of their vibration. At every level, from the smallest measurable scale to the largest observable structure, the universe turned out to be not just describable by mathematics, but apparently made of it. As though the physical world is a printout and the mathematics is the code. This video is about that code. About the 26-century-old idea that refuses to die, that keeps resurfacing in different languages, in different centuries, from Pythagoras to Plato to Galileo to Einstein to the theorists working right now in offices at Princeton and Cambridge and CERN. The idea that the universe is not a collection of things. It is a collection of relationships. And those relationships are mathematical. We will trace this idea from its origin in a Greek mystery school to its current form in the most advanced theoretical physics on Earth. We will ask why mathematics works at all. We will ask whether it was invented or discovered. And we will ask the question that sits beneath all of it, the one that most people never think to ask, because it sounds too simple to be important. If the universe is made of mathematics, then what is mathematics made of? The story begins, as the best stories in the history of ideas often do, with a sound. Pythagoras of Samos, born around 570 BC on a Greek island in the eastern Aegean, was walking past a blacksmith's forge when he heard something that stopped him in the street. The hammers striking the anvils were producing sounds that were not random. Some combinations were harmonious, others were dissonant, and the difference, he realized, was not a matter of taste or preference, it was a matter of proportion. The hammers that produced pleasing intervals had weights that stood in simple numerical ratios to one another. 1 to 2, 2 to 3, 3 to 4. The story may be apocryphal. The physics of hammer acoustics does not quite work the way the legend suggests. But what Pythagoras did next is not legend. It is documented. He went home and built a monochord, a single-stringed instrument, and began experimenting. He divided the string at different points and plucked it, and what he found was one of the most consequential observations any human being has ever made. When you divide a vibrating string exactly in half, the resulting note is 1 octave higher than the original. The ratio is 2 to 1. When you divide it in a ratio of 3 to 2, you get a perfect fifth, the most consonant interval in music. A ratio of 4 to 3 produces a perfect fourth. The relationships that the human ear experiences as beautiful, as harmonious, as resolved, as right, are not subjective. They are mathematical. They are ratios. They are numbers. And this shattered something in Pythagoras' understanding of the world. Because if the experience of beauty, something that feels as personal and ineffable as anything a human being can perceive, turns out to be governed by numerical ratios, then what else might be? What if the ratios are not confined to music? What if they extend to everything? What if the entire universe, from the motion of the planets to the structure of matter to the cycles of birth and death, is organized by the same kind of hidden numerical order? This was the birth of an idea that would never die. Pythagoras did not merely propose that mathematics was useful for understanding the world. He proposed that mathematics was the world. That number was not an abstraction imposed on reality by the human mind, but the fundamental substance of reality itself. All is number. That was the central doctrine of the Pythagorean school. And it was not a casual philosophical position. It was a revelation, a sacred principle, the foundation of an entire way of life. The Pythagorean school, established in Croton in southern Italy, was not a university in any modern sense. It was a mystery school, part philosophical academy, part monastic community, part secret society. Its members followed strict dietary rules, practiced communal living, observed periods of ritual silence, and were bound by oaths of secrecy. The inner circle was known as the mathematikoi, literally, those who learn. Mathematics, for the Pythagoreans, was not an academic discipline. It was a spiritual practice, a form of purification, a method for aligning the individual soul with the mathematical order of the cosmos. And the cosmos, they believed, was ordered. Not chaotically, not approximately, perfectly. The distances between the planets, they proposed, corresponded to musical intervals. The movements of the celestial bodies produced a sound, the music of the spheres, that was inaudible to human ears only because it had been playing since the moment of birth, and the ear had no silence against which to hear it. The universe was a symphony, and the score was written in numbers. Modern astronomers would eventually confirm that the distances between planetary orbits follow certain mathematical patterns, not the exact ones Pythagoras proposed, but patterns nonetheless. Johannes Kepler, 2,000 years later, would spend his career searching for the geometric harmonies of planetary motion and would discover them, encoded in the elliptical orbits and the precise mathematical laws that govern them. Kepler considered himself a Pythagorean. He believed he was finishing what Pythagoras had started. But the most enduring legacy of Pythagoras is not any specific discovery. It is the posture, the orientation, the willingness to look at the physical world and ask, what is the mathematics underneath? To assume, as a starting axiom, that the universe is not random, not chaotic, not arbitrary, but structured, and that the structure is mathematical, and that the role of the human mind is not to impose order on chaos, but to discover the order that was already there. Every physicist alive is working within this assumption. Every equation written on every blackboard in every physics department on Earth is an act of faith in the Pythagorean proposition, that the universe is rational, that it is structured, that it answers to mathematics. And that proposition, first articulated in a Greek forge 26 centuries ago, has never once been disproven. It has only been confirmed, again and again and again. Before Pythagoras, music was a mystery. It was understood as a gift from the gods, something divine, something that moved the soul through channels that reason could not trace. You heard a melody, and something inside you responded, not intellectually, physically, emotionally, in a place that seemed to have nothing to do with logic or calculation. And then, a man with a single string and a measuring device showed that the thing moving your soul was a ratio. 2 to 1 produces an octave. 3 to 2 produces a fifth. 4 to 3 produces a fourth. These are not approximations. They are exact. The intervals that human beings across every culture, every era, every continent have experienced as consonant, as resolved, as beautiful, as complete, correspond to the simplest possible numerical relationships. And the intervals experienced as dissonant correspond to more complex ratios. The experience of harmony is not subjective. It is mathematical. It is built into the physics of vibration itself. Consider what this means. Music is arguably the most emotional, the most irrational, the most inexplicably moving form of human expression, It bypasses the intellect entirely. It reaches into the body and the nervous system and does something that language cannot do. And yet, at its foundation, at the level of the vibrating string, the oscillating air column, the resonating membrane, it is pure number, pure ratio, pure mathematics performing itself as sound. The Pythagoreans understood this as evidence, not just of a mathematical curiosity, but of a cosmological principle. If the most seemingly irrational human experience, beauty, turns out to be governed by precise numerical relationships, then the boundary between the rational and the irrational is not where you think it is. Then mathematics is not a cold, abstract, inhuman domain opposed to feeling. It is the hidden structure of feeling itself. And the evidence extends far beyond the monochord. Every musical instrument on Earth operates on the same principle. The Overtone series, the sequence of harmonics that gives every instrument its distinctive timbre, is a mathematical sequence. It is the same sequence everywhere, for every vibrating body governed by the same physics. A violin in Vienna, and a bamboo flute in Bali, and a bronze bell in Kyoto are all producing sounds that are organized by the same mathematical relationships. The cultures are different, the traditions are different, the mathematics is identical. This is not an accident, and it is not a human invention. The Overtone series is not a scale that somebody decided on. It is a physical law. It is what happens when any object vibrates. The universe itself generates these ratios. They are embedded in the physics of wave motion, in the way energy propagates through a medium, in the fundamental mathematics of oscillation. Human music does not impose mathematical structure on sound. It discovers the mathematical structure that was already there and organizes it into art. And here is the implication that extends far beyond music. If the structure of sound is mathematical, if the thing you experience as beauty when you hear a chord resolve is the subjective experience of a numerical relationship, then what else in your experience might be mathematics in disguise? What other feelings, perceptions, intuitions might turn out, under examination, to be the inner experience of an outer equation? The golden ratio appears in the proportions of the human face that are perceived as most attractive. It appears in the spiral of a nautilus shell. It appears in the arrangement of petals on a flower, in the branching of trees, in the spiral arms of galaxies. Wherever the eye registers beauty, mathematics is lurking underneath. Not because the eye was trained to find mathematical beauty, because beauty and mathematics may be the same thing, experienced from different sides. This was the first crack in the wall, the first moment where someone looked at the world and saw, beneath the surface of sensory experience, a hidden layer of numerical order, and the crack has never been repaired. Every subsequent advance in science, every equation that predicted the motion of a planet, the behavior of a wave, the structure of a crystal, has widened it. The wall between the mathematical and the physical has been thinning for 26 centuries, and what Pythagoras found with a single vibrating string, modern physics has found at every scale of existence. The universe is not merely described by mathematics, it sings in mathematics. And the human ear, for reasons that no theory of evolution has fully explained, can hear the song. Pythagoras proposed that the universe is made of number. His most famous student, or rather his most famous intellectual descendant, asked the next question. If the universe is made of number, then what is the physical world? What is matter? What is the thing you can touch and see and weigh if the fundamental reality underneath it is mathematical? Plato's answer, delivered in the 4th century BC, remains one of the most radical propositions in the history of human thought. The physical world, he said, is not the real world. It is a shadow, a projection, a degraded copy of something more perfect, more permanent, more real, a realm of ideal forms that exists beyond the reach of the senses and is accessible only through the intellect. The allegory of the cave. Perhaps the most famous thought experiment in Western philosophy makes the argument vivid. Imagine prisoners chained in an underground chamber, facing a blank wall. Behind them, a fire casts shadows of objects carried along a raised walkway. The prisoners see only the shadows. They believe the shadows are reality. They name them, categorize them, argue about them. Their entire world is a wall of flickering images. Now imagine one prisoner is freed. He turns around. He sees the fire, the objects, the mechanism that produces the shadows. He is disoriented. The light hurts. The real objects look strange, less familiar, less comfortable than the shadows he has known all his life. But gradually his eyes adjust, and he realizes that everything he believed was real was a projection of something he could not see. For Plato, the shadows are the physical world. The objects casting them are the forms, the ideal, eternal, mathematical structures that underlie physical reality. A circle drawn on paper is not a true circle. It is an approximation, imperfect, temporary, contingent. The true circle exists in the realm of forms. It is the mathematical definition of circularity itself, perfect, unchanging, independent of any physical instantiation. And the drawn circle is a shadow of that form, projected into the imperfect medium of matter. This sounds abstract. It sounds like the kind of thing a philosopher says when they have spent too long thinking and not enough time living. But consider what modern physics has discovered. The electron is not a thing. It is a solution to an equation. A mathematical object defined by quantum numbers, described by a wave function, existing as a probability distribution until the moment of measurement collapses it into a specific outcome. The equation is permanent. The physical electron is temporary, contextual, dependent on observation. Which one is more real, the equation or the particle? Plato would say the equation. And a disturbing number of contemporary physicists would agree. The physicist Max Tegmark has argued explicitly for what he calls the mathematical universe hypothesis. The idea that the universe does not merely have mathematical properties, but is a mathematical structure. That there is no physical stuff underlying the mathematics. The mathematics is the stuff. The physical world, the world you touch and see and navigate every day, is what mathematics looks like from the inside. If Tegmark is right, then Plato was not a mystic. He was an early physicist who happened to arrive at the correct ontology 24 centuries before the instruments existed to test it. The cave was not a metaphor. It was a description. And the shadows on the wall, The physical objects you believe are the furniture of reality are exactly what Plato said they were, projections of a deeper mathematical order that your senses are not equipped to perceive directly. The question, of course, is whether this is true. Whether mathematics really is the bedrock of existence or merely the best tool for describing it. Whether the map and the territory are the same thing. Or whether the astonishing success of mathematics is just a coincidence. A lucky fit between the structure of the human mind and the structure of the world. That question will follow us for the rest of this video. But before we can answer it, we need to understand just how astonishing the fit actually is. For 2,000 years after Pythagoras, the idea that the universe was mathematical remained a philosophical position. Beautiful, compelling, but ultimately untestable. You could believe it or not. You could argue for it in a symposium or dismiss it over wine. It had the status of a vision. Profound, perhaps, but not yet proven. Then Galileo Galilei pointed a telescope at the sky, and everything changed. Galileo did not merely observe the heavens. He measured them. He timed the swinging of pendulums and discovered that the period depends on the length of the string in a precise mathematical relationship. He rolled balls down inclined planes and discovered that the distance traveled increases as the square of the time elapsed. He dropped objects and found that gravity accelerates all bodies at the same rate, regardless of mass. A finding that contradicted Aristotle and confirmed that nature follows mathematical law, not intuitive expectation. And then he wrote the sentence that redrew the boundary between philosophy and science forever. The book of nature, he said, is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. This was no longer Pythagorean mysticism. This was empirical. This was measurable. This was a man standing in a laboratory with instruments saying, "I have checked, and the mathematics works. The universe does what the equations say it will do, not approximately, exactly, to as many decimal places as your instruments can measure." Isaac Newton, born the year Galileo died, took this further than anyone could have imagined. In a single work, the Principia Mathematica, published in 1687, he demonstrated that the same mathematical law governs the falling of an apple and the orbit of the moon. That the force of gravity between any two objects in the universe can be calculated with a single equation. That the trajectories of comets, the tides of the oceans, the precession of the equinoxes, phenomena that had been observed for millennia without explanation, all follow from the same handful of mathematical principles. The universe was not just written in the language of mathematics, it was obedient to it, and the obedience was unreasonable. That is the word that would later be used by the physicist Eugene Wigner in his famous 1960 essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Why should abstract mathematical structures, developed by human minds for their own internal consistency, turn out to describe the physical universe with such terrifying precision? Why should an equation derived on paper in a study predict the behavior of a particle that has never been observed, in conditions that have never been created, with accuracy to 12 decimal places? Newton's laws did exactly this. They predicted the existence of a planet, Neptune, before anyone had seen it, purely from mathematical analysis of perturbations in the orbit of Uranus. The mathematics said there must be a massive body at a specific location in the sky. Astronomers pointed their telescopes there. And there it was. A planet discovered not by observation, but by equation. The mathematics reached into the darkness and found something that no eye had ever seen. This was the moment the Pythagorean idea stopped being philosophy and became power. Mathematics was not just a description of the universe. It was a prediction engine, a tool for reaching into the unknown and pulling out facts. A language that, when spoken correctly, the universe answered. And the answers kept coming. Maxwell's equations unified electricity, magnetism, and light into a single mathematical framework and predicted the existence of radio waves before anyone had detected them. The periodic table, organized by mathematical patterns in atomic structure, predicted the properties of elements that had not yet been discovered. Dirac's equation, a purely mathematical exercise in combining quantum mechanics with special relativity, predicted the existence of antimatter, a form of matter no one had imagined, confirmed experimentally 4 years later. Again and again, the same pattern. A mathematician or physicist writes down an equation to satisfy the internal logic of the mathematics, and the universe turns out to contain exactly what the equation describes. The mathematics arrives first. The physical reality follows. As though the equation is not describing the universe, but instructing it. As though the code is being read. Galileo said the book is written in mathematics. Newton proved it could be read. And every physicist since has been turning pages, finding at every scale the same astonishing correspondence between the abstract and the real. The question is no longer whether mathematics describes the universe. The question is why. There is something about the universe that goes beyond the mere fact that mathematics describes it. Mathematics does not just describe the universe the way a map describes a territory, approximately, partially, from a certain angle. Mathematics describes the universe the way a blueprint describes a building, completely, structurally, from the inside out. And the reason for this has to do with something that most people have never heard of, but that physicists consider the deepest insight in all of theoretical physics. Symmetry. Not the everyday kind, not the symmetry of a face or a butterfly wing. Mathematical symmetry. The kind that says, if you change something about a system in a specific way, and the system does not change, then there is a symmetry present. And wherever there is a symmetry, there is a conservation law. Energy is conserved because the laws of physics do not change over time. Momentum is conserved because the laws of physics do not change from one location to another. Angular momentum is conserved because the laws of physics do not change when you rotate the system. This connection between symmetry and conservation was proven in 1918 by Emmy Noether in a theorem that Albert Einstein described as the most important mathematical achievement in the history of physics. It is not an exaggeration to say that Noether's theorem is the reason modern physics works, because it means that the fundamental laws of the universe, the rules governing everything from the decay of a particle to the expansion of space, are not arbitrary. They are consequences of mathematical symmetries. The laws are not imposed on the universe from outside. They emerge from the internal mathematical structure of the universe itself. Think about what this means. The universe does not obey rules because someone wrote the rules. It obeys rules because its mathematical structure makes those rules inevitable. Conservation of energy is not a commandment. It is a geometric consequence. The behavior of every particle, every field, every force in nature is a reflection of an underlying symmetry. And the symmetry is purely mathematical. And the symmetries go deeper than anything Pythagoras could have imagined. The standard model of particle physics, the most successful physical theory ever constructed, confirmed by every experiment performed over the past 50 years, is built entirely on symmetry groups. SU3 for the strong force, SU2 for the weak force, U1 for electromagnetism. These are not physical objects. They are abstract mathematical structures, groups of transformations that leave certain properties invariant. And the particles that make up everything in the universe, quarks, leptons, bosons, are classified not by their physical properties, but by their mathematical representations within these groups. The universe is not just described by mathematics. It is organized by it. The fundamental forces are expressions of mathematical symmetry. The particles are representations of mathematical groups. The laws are consequences of mathematical invariance. Strip away the physical language, and what remains is pure structure, pure relation, pure number. Eugene Wigner called this unreasonable. Why should abstract mathematical structures, invented by human minds for the pleasure of internal consistency, map onto the physical universe with such precision? Why should a symmetry group discovered by a mathematician in the 19th century turn out to be the organizing principle of subatomic reality? This is not a trivial question. It is, in many ways, the deepest question in all of science. And there are only two possible answers. Either the correspondence between mathematics and physics is a cosmic coincidence, the most spectacular accident in the history of existence, or it is a clue. A hint that mathematics and physics are not separate domains brought together by human ingenuity, but aspects of the same underlying reality. That the reason mathematics describes the universe so well is that the universe is mathematical, not as a metaphor, as an ontological fact. Pythagoras said, "All is number." Noether proved that the laws of nature are consequences of mathematical symmetry. And the Standard Model demonstrated that the catalog of everything that exists can be written as a table of mathematical representations. The evidence has been accumulating for 26 centuries, and it all points in the same direction. Everything changed in the first decades of the 20th century. Not gradually, not through a steady evolution of understanding. It changed the way a floor changes when a trapdoor opens, suddenly, completely, and with the sickening sensation that what you were standing on was never as solid as you believed. Quantum mechanics did not refine the classical picture of reality. It replaced it. And what it replaced it with was not a new physical picture. It was mathematics. Before quantum mechanics, physics described a universe of objects. Particles had positions. They had trajectories. They existed in definite states at definite locations. The mathematics was a tool for tracking these objects, for predicting where they would be and what they would do. The objects were real. The mathematics was a description. Quantum mechanics inverted this relationship entirely. In the quantum world, particles do not have definite positions until they are measured. Before measurement, they exist as wave functions, mathematical objects that encode the probability of finding the particle in any given state. The wave function is not a physical thing. It is a mathematical function. It lives not in physical space, but in an abstract mathematical space called Hilbert space. And yet it is the most complete description of the particle that exists. There is nothing behind the wave function, no hidden object waiting to be found. The mathematics is the most fundamental layer. Below it, there is nothing. The double slit experiment made this unbearable. A particle, an electron, a photon, even a molecule, is sent toward a barrier with two slits. If it were a classical object, it would pass through one slit or the other. It does not. It passes through both simultaneously. It interferes with itself, producing a pattern on the detector screen that is only possible if it traveled through both paths at once. But if you place a detector at the slits to determine which path it took, the interference disappears. The particle behaves as though it passed through only one slit. The act of measurement changes the outcome. Not the physical act of interacting with the particle, the act of obtaining information about it. The universe, at the quantum level, appears to respond to the question being asked. And the response is not physical. It is mathematical. The wave function collapses. The probability distribution resolves into a definite outcome. The equation delivers its answer. Werner Heisenberg, one of the founders of quantum mechanics, was explicit about what this meant. He said that the atoms and elementary particles are not real in the same sense as the objects of daily life. They form a world of potentialities and possibilities rather than one of things and facts. The most fundamental constituents of the universe are not physical objects. They are mathematical possibilities. The physical world, the world of definite outcomes, of solid tables and measurable velocities, emerges from the mathematics, not the other way around. This is the point where many people stop and say, "This cannot be right. Matter is real. Objects are solid. I can touch this table, and all of that is true, at the macroscopic scale. But at the foundational scale, at the level where reality is being assembled, there are no tables. There are no objects. There are probability amplitudes, quantum fields, superposition states, and mathematical operators acting on abstract vectors in infinite dimensional spaces. The solidity of the world you experience is an emergent phenomenon. It is what mathematics looks like when enough of it accumulates." Niels Bohr said that physics is not about how the universe is, but about what we can say about the universe. The mathematics of quantum mechanics does not describe a world of objects. It describes a world of relations, correlations between measurements, probabilities of outcomes, mathematical structures that generate physical predictions with astonishing accuracy, but refuse to resolve into a picture of what is really there. And this is where Pythagoras returns. Because if the most fundamental description of reality is not a collection of objects, but a collection of equations, if the physical world emerges from mathematical structure rather than the other way around, then the proposition that the universe is made of number is not mysticism. It is the most straightforward interpretation of what quantum mechanics is actually telling us. The equations replaced reality, and nothing has replaced the equations. And then string theory arrived, and the circle that began with Pythagoras's monochord closed in a way that no one could have predicted. The central proposal of string theory is this: the fundamental constituents of reality are not point-like particles. They are one-dimensional vibrating filaments, strings, and the properties of every particle in the universe, its mass, its charge, its spin, its identity, are determined not by some intrinsic physical quality, but by the frequency and pattern of the string's vibration. An electron is a string vibrating in one mode. A quark is the same string vibrating in another. A photon is yet another mode. Every particle is the same fundamental entity, differentiated only by the mathematics of its vibration. The diversity of the physical world, the entire zoo of particles, the four fundamental forces, the richness and variety of everything that exists, emerges from a single kind of object playing different mathematical notes. Pythagoras said the universe is made of number. String theory says the universe is made of vibration, and vibration is number. Frequency is number. The mode of oscillation is number. The string is not a physical substance vibrating in a physical space. It is a mathematical structure, a one-dimensional object embedded in a 10 or 11-dimensional mathematical manifold whose vibrational modes are solutions to equations whose properties are determined entirely by the geometry of the space it moves through. The space itself, the extra dimensions that string theory requires, is not physical space as you understand it. It is compactified into structures called Calabi-Yau manifolds, six-dimensional geometric objects so complex that their mathematical classification remains incomplete. The shape of these manifolds determines the laws of physics. The geometry determines the particles. The topology determines the forces. Everything physical is a consequence of mathematical geometry. This is Pythagoras at cosmic scale. The monochord has become the string. The musical ratios have become vibrational modes. The harmony of the spheres has become the geometry of extra dimensions. And the proposition that all is number has become the working hypothesis of the most ambitious theoretical framework in the history of physics. String theory remains unproven. No experiment has yet confirmed or denied its predictions. It is, as its critics point out, a theory of extraordinary mathematical beauty that may have nothing to do with the actual universe. This is a legitimate concern, but the concern itself is revealing. Because the question it raises is, why should mathematical beauty be any guide to physical truth at all? Why should the most elegant equations tend to be the correct ones? Why should the universe care about the aesthetics of its own description? And yet it does. Again and again, in the history of physics, the mathematically beautiful theory has turned out to be the correct one. Maxwell chose his equations for their symmetry. Dirac chose his for their elegance. Einstein chose general relativity because it was the most geometrically natural description of gravity. And in every case, the beautiful mathematics turned out to describe the real world. If string theory is correct, then the universe is, at its foundation, a piece of music. Not metaphorically, structurally, a symphony of vibrating mathematical objects playing in a space whose geometry determines every note, producing a physical world that is nothing more and nothing less than the sound of the mathematics performing itself. Pythagoras heard it in a forge. 26 centuries later, string theorists are writing the score. There are approximately 26 fundamental constants in physics, numbers that appear in the equations governing reality: the speed of light, the gravitational constant, the mass of the electron, the charge of the proton, the strength of the strong nuclear force. These numbers are not derived from theory. They are measured. They are what they are, and physics cannot explain why they have the values they do. But it can explain what would happen if they were different. And the answer is nothing. Nothing would happen, because nothing would exist. If the gravitational constant were slightly larger, by a fraction so small it would not register on any human scale of magnitude, stars would burn through their fuel in a few million years instead of a few billion. There would not be enough time for planets to form, for chemistry to develop, for anything recognizable as life to emerge. If it were slightly smaller, stars would never ignite at all. The universe would be a cold, dark expanse of diffuse hydrogen, forever. If the strong nuclear force were 2% weaker, protons and neutrons could not bind together. No atomic nuclei, no atoms, no chemistry, no matter in any form beyond hydrogen. If it were 2% stronger, all hydrogen would fuse into helium in the first moments after the Big Bang. No stars, no water, no carbon, no life. If the mass of the electron were slightly different, the balance between electromagnetism and gravity that allows chemistry to function would collapse. Molecules would not form. If the cosmological constant, the number governing the expansion rate of the universe, were larger by 1 part in 10 to the power of 120, the universe would have expanded so fast that no structures could ever have formed. No galaxies, no stars, no planets, no observers. 1 part in 10 to the power of 120. That is not a fine margin. That is a margin so narrow that there is no analogy in human experience that captures it. It is as if someone set a dial with 10 to the power of 120 possible settings and placed it in the one position, the only position, that permits a universe capable of producing complexity, chemistry, and consciousness. This is the fine-tuning problem. And it is not a philosophical abstraction. It is a mathematical fact. The constants of nature are calibrated within ranges so absurdly narrow that their values appear, from a purely statistical standpoint, chosen. There are, broadly, 3 responses to this observation. The first is coincidence. The numbers happen to have the values they do. There is no deeper reason. We are simply lucky. This is logically possible but scientifically unsatisfying because the degree of luck required is so enormous that it dwarfs any improbability in the history of human thought. The second is the multiverse. Perhaps there are infinitely many universes, each with different values of the constants, and we necessarily find ourselves in one that permits our existence, because we could not find ourselves in one that does not. This is logically coherent. It is also, currently, untestable. And it raises its own mathematical question. What determines the distribution of constants across the multiverse? What is the meta-law? And is it mathematical? The third response is design. Not necessarily theological design, not a bearded figure setting dials, but structural design. The idea that the constants are not arbitrary because the universe is not arbitrary. That the values are consequences of a deeper mathematical structure that we have not yet discovered. A structure that, when understood, will reveal why these numbers must take these values, why no other values are consistent with the mathematics. This third response is the most Pythagorean. It says that the universe is not a collection of arbitrary parameters. It is a self-consistent mathematical structure, and the constants are as determined by that structure as the angles of a triangle are determined by its geometry. They could not be otherwise. Not because someone chose them, because the mathematics requires them. And if that is true, if the constants are not inputs but outputs, not settings but solutions, then the fine-tuning is not evidence of a designer. It is evidence of an equation so deep, so encompassing, so mathematically necessary that it produces, from its own internal logic, a universe precisely calibrated for complexity. Pythagoras would have recognized this idea immediately. The universe is not fine-tuned by a hand. It is fine-tuned by a number. There is a question that emerges naturally from everything we have discussed. A question that would have been inconceivable to Pythagoras, impossible for Plato, irrelevant to Newton, and is now, in the 21st century, the subject of serious academic debate. If the universe is mathematical, if its fundamental layer is not matter but structure, not substance but equation, then is the universe a computation? The simulation hypothesis, popularized by the philosopher Nick Bostrom in 2003, asks whether we might be living inside a computer simulation run by a more advanced civilization. The argument is statistical. If it is possible to create simulated universes with conscious inhabitants, and if advanced civilizations would have reason to create many such simulations, then the number of simulated universes would vastly outnumber the single real one, and the probability that we are in the real one, rather than a simulation, becomes vanishingly small. This argument has been critiqued on many grounds, but its deeper significance, the reason it has not been dismissed entirely, has nothing to do with science fiction. It has to do with the nature of mathematics itself. Because the simulation hypothesis is, at its core, a restatement of the Pythagorean proposition in computational language. If the universe is made of mathematics, and if mathematics can be computed, then the universe can be computed. And if it can be computed, the question of whether it is being computed becomes not absurd, but inevitable. The physicist John Wheeler, one of the giants of 20th century physics, the man who coined the term black hole, spent the final decades of his career pursuing an idea he called it from bit. His proposition was that every physical quantity, every particle, every field, every force derives its existence from information. That the fundamental substance of reality is not matter or energy, but binary information. Yes or no, on or off, 0 or 1. That physics, at its deepest level, is not about things. It is about answers to questions. Wheeler's proposal anticipated a revolution that is still unfolding. The physicist Erik Verlinde has proposed that gravity itself is not a fundamental force, but an entropic phenomenon, a statistical effect that emerges from the way information is distributed on surfaces. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind, suggests that the information content of any region of space can be encoded on its two-dimensional boundary, as though the three-dimensional universe is a projection of information written on a distant surface. Information, mathematics, computation. These words are converging, and the convergence points toward something that is either the most profound insight in the history of science or the most elaborate wrong turn ever taken. The insight is this: The universe may not merely be described by mathematics, or governed by mathematics, or structured like mathematics. The universe may be mathematics. Running, processing, computing itself into existence, one quantum measurement at a time. This is not proven. It may never be proven, but it is remarkable that the trajectory of physics, from Pythagoras to Plato to Newton to quantum mechanics to information theory, has moved consistently in one direction, away from the physical, toward the mathematical, away from stuff, toward structure, away from the idea that the world is made of things, and toward the idea that the world is made of relationships, patterns, and information. And if that trajectory continues, if the next revolution in physics follows the same pattern as every previous one, then what we are approaching is not a new theory of matter. It is a theory of mathematics itself. A theory that explains why there is something rather than nothing by explaining that something is what mathematics does when it is sufficiently complex. That existence is computation. That reality is a proof. Pythagoras stood on a Greek island and said the universe is made of number. 26 centuries of physics have not disproven him. They have only made his claim more precise. Long before mathematics became a formal discipline, long before the first equation was written, the first proof constructed, the first theorem named, human beings were drawing the mathematics of the universe on the walls of their temples. The flower of life appears in the temple of Osiris at Abydos, carved into granite over 3,000 years ago. It appears in Chinese temples, in Indian temples, in medieval European manuscripts, in Islamic mosques, in the synagogues of Galilee, in Leonardo da Vinci's private notebooks. The same pattern, a series of overlapping circles arranged in a hexagonal lattice, recurring across civilizations that had no contact with one another, separated by oceans and millennia. This is not coincidence. And it is not cultural diffusion, it is convergence. Multiple civilizations, working independently, arrived at the same geometric pattern because the pattern is not a human invention. It is a mathematical structure inherent in the geometry of space itself. It is what happens when circles of equal radius are packed most efficiently on a plane. It is the natural geometry of closest packing, the same geometry that governs the arrangement of atoms in a crystal, the cells in a honeycomb, the seeds in a sunflower head. The ancients did not know atomic physics. They did not know crystallography. But they saw the pattern. They recognized it as fundamental, and they encoded it in their most sacred spaces, not as decoration, but as information. As a message about the mathematical structure of reality, written in the only universal language available, geometry. The Platonic solids, the 5 regular polyhedra that Plato associated with the elements of nature, were known to the Pythagoreans and appear in carved stone objects from Scotland dating to at least 2000 BC, 1,000 years before Plato was born. These 5 shapes, tetrahedron, cube, octahedron, dodecahedron, icosahedron, are the only convex polyhedra whose faces are identical regular polygons. They are mathematically unique. They are also, as it happens, the shapes that appear spontaneously in nature. In crystal structures, in viral capsids, in radiolarian skeletons, in the geometry of molecular orbitals. Islamic geometric art, developed over centuries in mosques from Spain to Central Asia, contains tessellations that were not formally described by Western mathematics until the work of Roger Penrose in the 1970s. Penrose tilings, periodic patterns that fill a plane without repeating, appear in the tile work of the Darb-e-Imam shrine in Isfahan, Iran. The shrine was built in 1453. Penrose published his discovery in 1974. 5 centuries separated the art from the mathematics. The art came first. Hindu and Buddhist mandalas encode mathematical symmetries, rotational, reflective, translational, that correspond to the symmetry groups used in modern particle physics. The mandala is not a random arrangement of pretty shapes. It is a map of symmetry, a visualization of the mathematical structures that, as Noether proved, underlie the conservation laws governing everything in the physical universe. Gothic cathedrals were designed using geometric proportions derived from the golden ratio and the square root of 2. The same proportions that appear in the spiral arms of galaxies, in the growth patterns of nautilus shells, in the arrangement of leaves on a stem. The cathedral builders did not know astrophysics, but they knew the proportions felt right. They knew that certain ratios produced a sense of harmony, of elevation, of something sacred. And the ratios they chose are the same ones that modern science finds embedded in the architecture of nature. All of this points to something that the modern world has been slow to recognize. The ancient civilizations that encoded geometric patterns in their sacred architecture were not being decorative. They were being precise. They had identified, through observation, through meditation, through whatever process of deep attention their traditions cultivated, the mathematical structures that underlie physical reality. And they recorded them in stone, in tile, in paint and gold leaf and carved granite, in a language that does not require translation because it is the same language the universe speaks. Sacred geometry is not mysticism. It is Pythagoreanism preserved in architectural form. The pattern behind the pattern. The number behind the shape. The code that keeps appearing in every culture, in every century, because it is not a human creation. It is a universal structure. And the human mind, when it looks carefully enough, cannot help but find it. There is a shape that contains infinity inside a finite boundary. It is not a theoretical curiosity. It is not an abstract mathematical toy. It is the shape of the universe itself. In 1980, Benoit Mandelbrot generated a computer image of a set defined by a simple iterative equation. Take a complex number, square it, add a constant, and repeat. The resulting boundary, the Mandelbrot set, is the most complex mathematical object ever visualized. It is infinitely detailed. You can zoom in forever and find new structures at every scale. Spirals, filaments, miniature copies of the whole set nested within its edges. Each one slightly different, each one infinitely complex in its own right. There is no end to it. A simple rule, applied recursively, produces infinite complexity. And the universe does the same thing. Look at a fern. Each frond is a miniature copy of the whole fern. Each sub-frond is a copy of the frond. The same pattern repeats at every scale, not identically, but self-similarly. This is a fractal. Look at a tree. The branching pattern of the trunk into major limbs into branches, branches into twigs. The same geometry repeats at every level. Look at your lungs. The bronchial tree divides and subdivides in a fractal pattern that maximizes surface area within a finite volume. Look at a river delta from above. Look at a lightning bolt. Look at the distribution of galaxies in the observable universe. The same branching, self-similar, fractally recursive patterns appear everywhere. Not because someone designed them that way, because fractal geometry is the most efficient way to fill space, distribute resources, and maximize surface area. It is mathematically optimal. And nature, which has no interest in aesthetics but a profound interest in efficiency, converges on it again and again. The Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, 21, is a related phenomenon. It appears in the spiral arrangement of sunflower seeds, in the breeding pattern of rabbits, in the number of petals on most flowers, in the spiral of a nautilus shell, in the proportions of the human body. The ratio between consecutive Fibonacci numbers converges on the golden ratio, approximately 1.618. A number that appears in the geometry of the pentagon, the icosahedron, the DNA double helix, and the orbital resonances of planetary systems. Why? Why should a single number, an irrational number no less, a number whose decimal expansion never terminates and never repeats, appear in the structure of a seashell and the structure of a galaxy? Why should the same ratio govern the growth of a sunflower and the spiral of a hurricane? Why should the mathematics of a simple recursive sequence map onto the physical architecture of the living world? The Pythagorean answer is the simplest one. Because the universe is mathematical, and mathematical structures, when they are deep enough, are universal. They do not belong to any one domain. They are not confined to biology or physics or architecture. They appear wherever the conditions are right for them to appear, which, in a mathematical universe, is everywhere. Fractals are the clearest evidence of this universality. A simple rule, iterated, produces infinite complexity. A simple equation, applied recursively, generates structures that mimic the geometry of nature at every scale. The correspondence is not approximate. It is exact. The mathematical fractal and the natural fractal are the same structure, one made of numbers, the other made of matter. And the matter, as quantum mechanics has shown, is itself made of numbers. The universe is not just mathematical at the foundational level. It is mathematical at every level. The same patterns, the same ratios, the same recursive geometries repeat from the quantum to the cosmic. The fractal is the signature. And the signature says, "This was not assembled from parts. This was generated from a rule." In 1931, a 25-year-old Austrian mathematician named Kurt Gödel published a paper that shattered the foundations of mathematical certainty. It is, by many accounts, the most important result in the history of logic. And its implications for the question we have been asking, whether the universe is made of mathematics, are as profound as they are disturbing. Gödel proved two theorems. The first says that in any consistent mathematical system, complex enough to describe basic arithmetic, there will always be statements that are true but cannot be proven within the system. The second says that no such system can prove its own consistency. Mathematics, in other words, cannot fully know itself. There will always be truths that are real, that are valid, but that the system cannot reach from within. This is not a technical limitation. It is not a matter of insufficient computing power or imperfect axioms. It is a structural property of mathematics itself. It is a wall built into the architecture of logic. And no advance in mathematics, no new axiom, no new method, no new language can remove it. Gödel proved that the wall is permanent. For the program of using mathematics to completely describe the universe, this is a profound complication. If the universe is a mathematical structure, and if Gödel's theorems apply to that structure, then there are truths about the universe that cannot be derived from within it. There are facts about reality that are real, that hold, that matter, but that no equation, no proof, no calculation performed by any intelligence operating inside the system can ever demonstrate. This does not disprove the mathematical universe hypothesis, but it changes its character. If the universe is mathematics, it is not a mathematics that is transparent to itself. It is a mathematics that contains permanent mysteries, not because the mysteries are hidden, but because the structure of logic guarantees that some questions, even in a perfectly mathematical universe, have no answers that can be reached from inside. There is a strange echo here of something very old. Mystics across every tradition have described the ultimate nature of reality as knowable, but not through ordinary means, accessible, but not through logic alone, present but beyond the reach of the rational mind. The Tao that can be spoken is not the eternal Tao. The map is not the territory. The finger pointing at the moon is not the moon. Gödel proved, in the language of formal logic, what the mystics had intuited, that any sufficiently rich system of knowledge contains horizons that cannot be crossed from within. That knowing has limits, not practical limits, but structural ones. That the universe, if it is mathematical, is a mathematics that exceeds its own capacity for self-description. This is not a defeat for the Pythagorean vision. It is its deepest expression. Because it means that the mathematical universe is not a closed, finished, fully deterministic machine. It is an open structure, one that contains genuine mystery, genuine incompleteness, genuine room for what cannot be calculated or predicted or reduced to an equation. It is a mathematics that breathes. And that may be the most extraordinary finding of all. That in a universe made of number, there are truths that number cannot reach. That the code contains something the code cannot compute. That at the heart of the most rational structure imaginable, there is a space that reason alone cannot fill. We have arrived at the question that sits beneath everything. The question that Pythagoras implied but never asked directly. The question that Plato danced around with his realm of forms. The question that haunts every physicist who has ever written an equation that turned out to describe the world more accurately than they had any right to expect. Was mathematics invented by the human mind? Or was it discovered, found, like a continent, like a fossil, like a structure that was already there, waiting? If mathematics was invented, then its success in describing the universe is a coincidence, a spectacular world historical coincidence, but a coincidence nonetheless. We created a language. The language happened to fit the universe. We got lucky. The map happened to match the territory, not because the territory is a map, but because our map-making skills happened, through evolution or accident, or some unfathomable alignment of cognitive structure and physical structure, to produce an accurate representation. This view has defenders, serious, intelligent, well-informed defenders. They point out that mathematics is a human activity, performed by human brains, shaped by human cognitive constraints, that the mathematics we develop reflects the kinds of patterns our brains are capable of recognizing, and that our brains evolved to recognize the specific patterns present in the physical environment. The correspondence between math and physics is not a miracle. It is natural selection. We evolved to do the kind of mathematics that describes the kind of world we evolved in. End of mystery. But this explanation, satisfying as it sounds, runs into a problem. The mathematics that describes the quantum world, the world of superposition, entanglement, non-locality, probability amplitudes in complex Hilbert space, is not the kind of mathematics any organism would evolve to do. It is not intuitive. It does not correspond to anything in the environment of evolutionary adaptation. It describes a realm that no human sense organ can perceive, at scales that no human body ever encounters, using structures, infinite dimensional vector spaces, non-commutative algebras, spinor fields, that bear no resemblance to anything in ordinary experience. And yet it works. It works with a precision that exceeds any other theory in the history of science. The predictions of quantum electrodynamics are accurate to 12 decimal places, the most precise agreement between theory and experiment ever achieved by human beings. An agreement between an abstract mathematical structure and a physical measurement, using mathematics that no evolutionary pressure could possibly have selected for. If mathematics is an invention, this is inexplicable. If it is a discovery, it is expected. The physicist Roger Penrose has argued for decades that mathematical truths exist independently of human minds, that when a mathematician proves a theorem, they are not creating something new. They are uncovering something that was always true, that is true in the same way that the laws of physics are true, regardless of whether anyone is there to think about them. Penrose calls this mathematical Platonism, the view that mathematical objects and structures are real, that they exist in some sense that is independent of the physical universe, and that the human mind accesses them through a faculty that is not reducible to neural computation. This is a controversial position. Many philosophers of mathematics reject it. They argue that abstracta, numbers, sets, functions, do not exist in any meaningful sense outside the formal systems that define them. That mathematical truth is a property of axiomatic systems, not a property of reality. That the word real, when applied to a number, is a category error. But the universe keeps behaving as though numbers are real. As though the mathematical structure is the thing, and the physical world is its manifestation. As though Pythagoras was not speaking metaphorically when he said, "all is number," but literally. As though the map is not a description of the territory, but the territory itself, viewed from a different angle. The question remains open, and perhaps it must remain open. Gödel showed us that some questions cannot be answered from within the system. But the direction of the evidence, accumulated across 26 centuries, is not ambiguous. It points, with increasing force and increasing precision, toward the proposition that mathematics was not invented by the human mind. The human mind was invented by mathematics. And the universe in which that mind exists is not a physical thing decorated with mathematical properties. It is a mathematical structure that happens to produce, among its many consequences, the experience of being physical. We began with a man in a forge, hearing something in the sound of hammers that no one else had noticed. A pattern, a ratio, a hidden order that turned out to be not hidden at all, just unrecognized, sitting on the surface of the world in plain sight, waiting for someone to ask the right question. The question was simple. What is reality made of? And the answer that has been arriving in pieces for 26 centuries, from the monochord to the particle accelerator, from the Pythagorean mystery school to the mathematics department at Princeton, is increasingly clear. Reality is not made of matter. It is not made of energy. It is not made of any substance that your senses can detect or your hands can hold. Reality is made of structure, of relation, of pattern, of mathematics. The atoms in your body are described by equations. The forces that hold them together are consequences of symmetry. The particles that compose them are vibrations in quantum fields. Mathematical objects defined by their properties, not by any physical substance they are made of. The space they occupy is a geometric manifold. The time through which they move is a dimension in a four-dimensional mathematical structure. At every level, at every scale, the physical resolves into the mathematical. The concrete dissolves into the abstract. The substance yields to the structure. And the structure is beautiful. That is the part that continues to astonish. The equations that describe the universe are not merely accurate. They are elegant. They possess a symmetry, a parsimony, an aesthetic rightness that mathematicians and physicists have remarked on for centuries. Dirac said that a physical law must have mathematical beauty. Einstein chose between competing theories on the basis of their geometrical elegance. And again, the beautiful theory turned out to be the correct one, as though the universe has an aesthetic, as though it prefers certain kinds of mathematical structures over others, as though beauty is not a human projection onto reality, but a property of reality itself. Pythagoras would not have been surprised by any of this. He knew, or intuited, or perceived through whatever faculty the ancients used to arrive at truths that instruments would take millennia to confirm, that the universe is a mathematical object, that the physical world is the outermost layer of a structure whose inner layers are numerical, geometric, harmonic, that the experience of being alive in a physical body is what it feels like to be mathematics performing itself. And if that sounds cold, if the idea of a mathematical universe feels inhuman, mechanical, devoid of the warmth and mystery that makes existence feel meaningful, consider this. The mathematics is not a machine. It is not a dead mechanism grinding through calculations. It produced consciousness. It produced the ability to ask questions about itself. It produced a universe in which patterns can contemplate their own existence, in which equations can wonder what they mean. Whatever mathematics is, whatever this structure is that produces particles and fields and forces and ultimately minds capable of recognizing the structure, it is not lifeless. It is the most alive thing there is. Because everything that is alive is made of it. Everything that thinks is a consequence of it. Everything that loves, that creates, that struggles to understand. All of it is mathematics in motion. Pattern recognizing pattern. Structure reflecting on structure. The universe looking at itself through the temporary, improbable, mathematically inevitable lens of a human mind. Pythagoras heard the cosmos in the sound of a hammer. 26 centuries later, we hear it in the data streaming from particle accelerators and space telescopes and quantum computers. The instruments have changed. The signal has not. The universe is made of numbers, and the numbers somehow dream. If this video shifted something in the way you see the world, even slightly, even just enough to make you look at a spiral or a ratio, or the night sky with a different kind of attention, then the conversation worked. And conversations like this only continue if you help them continue. Subscribe. Not because I am asking, but because what we are building here is a library. A growing body of work that maps the places where science, philosophy, and the deepest questions about existence converge. If you found something in this video worth thinking about, the next one will go further. Leave a comment. Tell me what resonated. Tell me what you disagree with. The most interesting ideas in these videos often come from the conversations they generate, and your perspective might be the one that someone else needs to hear. And share this with someone who thinks about these things. Someone who lies awake, wondering whether there is a pattern underneath the noise. Someone who suspects, quietly, that reality is not what they were told. They need to know they are not alone in asking. Thank you for your time, thank you for your attention, and I will see you in the next one.